My name is Andrew Bird from Scale Up Systems, and I'll just be hosting today our guest webinar by Andrew Derrick of Pfizer. He's at Pfizer Sandwich in the UK. You can see a lot of details about his introduction there on the screen in front of you. He is actually a chemist, not a chemical engineer by training, so he's moved into the process engineer kind of role in the last couple of years.
Shown here some of the scale-up factors that we face, and they can be large, in some instances over 3,000 times increase in scale. So processes need to be well understood, and we need to predict what is actually going to happen on scale. So the DynoChem tools used in this work. I always start with the estimate UA utility whenever I'm doing any heat modeling work. You don't need any actual experimental data to use this tool. The utility estimates the heat transfer coefficient for jacketed vessels based on measurements for the vessel, the impeller, and the jacket. You need to know what the heat transfer fluid is used in the process and the process solvent. There are drop-down lists and the common solvents and systems in the actual physical property database built into the model. You can also look at the effect of jacket mixing on the overall UA and the impact of the actual physical properties of your reaction as well, if you overwrite some of the cells at the bottom of the results tab, which I can show you later. The tool that I normally move to next is the Fit UA tool. This is the one where you have actual experimental data from a target vessel, whether that's in the lab or the pilot facility here in the PDF in Sandwich, or a commercial facility. And I always find it useful to compare the results from the Fit UA tool with those of the Estimate UA tool, as it helps to identify root causes for the real-world jacket performance in the plant, and again we'll see some of that later on. I've yet to find a case where the two figures are actually the same. So the main model that's used in this work is the aptly named QR Scale-Up Imposed TJ model, which is found on the DynoChem Resources website. And you can use this model for semi-batch reactions which are dose controlled. The limitations here are really though that there is no kinetic description at all in the model, and then the assumption is the rate of reaction is far greater than the rate of addition, so it's a true dose controlled reaction. There's also no mixing sensitivity built into the model, so we can't have any meso mixing, and it's definitely not include a Bourne model. If the reaction is not dose controlled, then you need a reaction model, you need to use that. Assumption really here is that you can multiply the lab QR heat flow by a scale factor to get the plant QR profile. So you need a few more inputs for this model. You need the bulk, liquid, and the feed tank mass, volume, and heat capacity. You need the UA and coolant flow, and you can have obviously that from the estimate tool or from the fit tool. And obviously then you need the lab heat flow, QR, and TR and TJ profiles. I've shown here a real example from an RC1 calorimeter where the heat flow data is being measured and then transposed into the actual QR scale-up model itself. The benefits of using this tool is it's really quick to do scale-up calculations, and you really don't need any knowledge of the actual chemistry going on. It's the stretched and scaled QR from the actual RC1 one, and this is the predicted TR from those two events. You need a combination of the heat output and the jacket profile and the UA. And it's predicting a maximum temperature of 26.4 degrees. So what do we actually find? We actually found that, again, this is the real TJ response. We overimposed the QR, stretched and scaled QR, and there's the fit between the actual measured and observed, the measured and predicted temperature profile. And the actual TER max in this case was 26.3, so we're quite pleased with that. Bearing in mind this was the prediction was made from I can't remember 50-gram scale, and the actual commercial scale was 123 kilograms of the limiting reagent. So the conclusions for this was the initial UA estimation tool, and that approach of doing a risk assessment really helped select that 90-minute addition time. The interlock was appropriately in place at 28 degrees, and it wasn't required. And that fit UA data was actually very accurate and aided in excellent maximum TR predictions. So to conclude, I hope I've shown you that the DynoChem heat transfer tools, Estimate UA, Fit UA, and the QR scale-up models are really simple, quick models that can give pretty much a valuable insight to the plant jacket performance and can aid in simple heat balancing for dose-controlled semi-batch reactions. And even in the absence of actual plant performance data, the tools can facilitate risk assessment discussions during the process fitting exercise. This pretty much is routinely applied now for tech transfers from the lab to the commercial facilities. So, and both those steps that we've shown were successfully validated.